Yeah, hopefully we get more people in person, but if you can only make it through Zoom for whichever reason that might be, then I'm glad you made it either way. But we'll get started in about a half a minute. And it's time. Welcome back, folks, whether you came in through Zoom today or made it in person. I'm glad that you made it. For today's class, we're just moving further through section 13.3. We're looking into this confidence interval procedure right here, where we're estimating a proportion, specifically the population's proportion P. So we'll look into a couple more examples. One of the contexts we've seen it before in 13.2 when we did a very careful check of conditions. Another problem there is brand new. And for another brand new problem, quiz 9 is going to be heavily based off just doing the same 13.3 kind of confidence interval problems. So when you're solving quiz 9, you can use this section as a rough guide on how to go. And if you have any questions as you solve this one, don't hesitate to ask. For quiz number 8, this one's going to be due next class. This one's based off the chapter 10 problems that we were doing. So once we finish off section 13.3, we're changing gears into chapter 14, but we're not doing anything too different. As the scribbles on the Canvas page kind of indicates, it's nice to have a certain set of parallelism. What's remarkable is the format of these confidence interval formulas are very highly similar. Bigger difference is you have a different statistic here, y bar if you're estimating a population mean, and you have a statistic here, p hat, the sample proportion of successes, if you're estimating the population proportion of successes. They have different standard errors, as we recall as well. So we've been looking into this formula, and this will be the next formula when we're in the chapter 14. Well, aside from that, any questions or comments at the moment, folks? Okay, and other thing I want to mention is usually I get to Friday where I start to post the exam information. Shouldn't have wiped that out yet. Our third exam is Monday, November 17th, but I had some extra time today to put in some work on the exam information and review material. And also I know that we're not going to get very far to chapter 14, so I know pretty much where we're going to end up this week. So that tells us we have a good idea what's going to be exam 3. It's going to be officially these chapters. It'll be chapter 7. This is the regression analysis problem, where you're using the least squares regression line to make observations and predictions and so on. Chapter 10 is all about statistics versus parameter, observational studies versus a design experiment. And chapter 13, there's really going to be two problems from chapter 13. First problem is like section 13.2, where we're checking the conditions very, very carefully. And the second problem in chapter 13 will be like the quiz number 9, where we're mainly focusing on doing the whole confidence interval and giving a strong conclusion. So one question for chapter 7, chapter 10, but chapter 13 is pretty big. There's lots of ideas. I'm not going to ask a direct question in 13.1. This is mostly a big conceptual section where we're putting ideas together, where we first took a look at the central limit theorem. The major question is going to be 13.2, checking conditions thoroughly, and 13.3, the full confidence interval. So this got posted early. If you are the kind of person that likes to study these early, we have the same kind of sample exams, version 1, version 2. We'll talk more about these when we get back next week. Major thing we'll probably mention a couple times is on the 13th, ahead of the exam on the 17th, I'll call for questions from class once again, and we could have a bona fide official review, unofficial review day if lots of questions come up, just like before. But I think that's my full spiel of announcements today. Any questions or comments at the moment, folks? Okay, Christian's kind of in the hot seat today since he's the only one that made it to class. So I'll probably look at the camera as well, so I'm not just staring you down the whole time asking for questions. But let's get started. So we're on example 3 in section 13.3. And here's where we left off. So this one, again, is a problem that we looked into before. Major thing we looked into on this one was very thoroughly checking the conditions, which means this is kind of redundant. Are the conditions for match for the large sample confidence interval? But we'll do this in kind of a brief way so it doesn't feel like we're doing the same kind of problem twice. So as far as the conditions, it's going to be these that we're going to be looking into here. We're just going to check these two conditions thoroughly. But I was just telling Christian that it's going to be kind of a weird class. He's the only one that made it, so I'm glad you made it as well. We have a big Zoom class today, so several people. No one doing a classroom observation, so just classmates in Zoom today. So let me post this here just as a reminder. This is all we're doing for the condition checking, just looking into conditions 1 and 2. So it's kind of a redo of the example 2 that we did before. First thing we should do to get through this kind of problem is first read through the context. To evaluate the policy of routine vaccination for infants for the whooping cough, not the whooping cough, the whooping cough, adverse reactions were monitored in 339 infants. That tells us a sample size in this problem is n equals 339, who received their first injection of the vaccine. So the problem is about adverse reactions, and we're told reactions were noted, adverse ones, in 20.35% of the infants. This study just tells you the statistics straight out. P hat is 0.2035. And another thing you might want to note in the margin quickly is that a success is the outcome of having an adverse reaction. So this gets us started. We'll describe the parameter, briefly check the conditions, just looking into condition 1, condition 2 from the full procedure that we saw up there in the notes. And let's start off with the parameter P. It just says unknown parameter, but because this is categorical data, we'll write it out as P equals the true proportion of, you can mention either the population or the successes first, but so far in these notes, we've only mentioned the successes first. So let's keep that as just kind of a pattern of attack for this parameter. It's going to be the true proportion of adverse reactions I think we can be a little bit more specific if we liked. If you just said adverse reactions, I think this is enough context already. But you could say specifically adverse reactions to the vaccine. I didn't say which vaccine, but we know we're talking about the whooping cough. In 1943, they administered this vaccine. So that right here mentions the successes. Now we have to mention the population as well to say exactly what the parameter is. The parameter describes the population, so it's part of its description. True proportion of adverse reactions to the vaccine for all infants in this country. So this part is the population. So you could reverse engineer this by reading the study and determine the country was actually Great Britain, learn a whole lot about this problem. But if you just said all infants and you didn't even say in this country, that would have been okay as well, because the problem is pretty vague whether this is a global study or a national study, or maybe they're just looking into one county in Idaho. They didn't really tell us. So do the best you can with the context you're given. You don't have to be hyper specific, but try to pull in the context by mentioning things like the fact that we're talking about adverse reactions to a vaccine, and the population is fundamentally all infants. So that's hitting the context really hard with those parts there. Well, that's another look at writing down this parameter. I don't recall if we said it verbatim exactly the same, but I believe we captured the same essence when we did this last time. Next thing is briefly checking the conditions. And this is kind of confusing in a way because we're looking at just two conditions. But when we did this before, there were four conditions and only three that we majorly checked. And the idea behind that was in section 13.2, the major thing we were studying was the central limit theorem itself. Sorry, try to move this window. Not playing too nice. Oh, there we go. The central limit theorem itself is a pretty big statement. And we were checking the conditions of that central limit theorem. These same conditions import right back into the method that we're looking into. But the method that we're looking into just paraphrases it down to these two reduced conditions, the things we can actually verify from the information given. So in a certain sense, they're slightly different problems. This is more about verifying the central limit theorem. Our confidence interval is built on the central limit theorem, but these are the two major things that we'll check. And as an exam question, I probably would take this part off and just like we mentioned, split this as a whole different question if we're checking these three conditions in a different problem. Or else the problems tend to get a little large. But just for the reminder on how this goes, it says there was 339 infants, but no information on how they got in the study. So for part one, we'll say it is unknown if the sample is random. It probably was. It's at least probably a representative sample. That's what they're mentioning here, if it was a study that was published in the Lancet. But from what we know, that's just not something they told us directly. For part two, the conditions of the confidence interval, we check if we have enough successes and enough failures. We need at least 10 successes, 10 failures. And it kind of feels redundant. We looked at this before in the section 13.2, but just a reminder, let's do it again. If they give us a p-hat value, we actually use these two equations down below. We take n times p-hat. The sample size n above is the 339 times 0.2035. This one doesn't come out as an even integer, so we just round to the nearest integer. So take 339.2035, and the nearest whole number would be 69. So we had 69 successes in this problem. And let's say what that was, 69, which is greater than or equal to 10 successes. And we can do n times 1 minus p-hat. The way we did it before was take n minus the 69 successes, just as a faster way to do the same result, and get 339 minus 69 equals 270, which is also greater than or equal to 10. That's what we wanted, failures. So this told us by part two, the sample size is large enough. So that's our major conditions that we were checking. We have an unknown on condition one, whether the sample is random. We do know if it is a random sample, conditions, these two conditions are met at least, because the sample was large enough to produce the right amount of successes, right amount of failures. So you could end the problem right here, but sometimes it's good to give just an overall assessment. And so that's why I usually write personally overall. The conditions are met, provided the sample was random. So that's our second look at the conditions. If I thought about this a little bit ahead of time when I wrote out these notes, I probably wouldn't have done the part B on this one because we did all three parts right here for the same problem in section 13.2. So it is a little redundant. Sorry about that. But it's another look at it. So extra practice is the good outlook on it. Any questions at all, folks, with part B? Okay, so now is the more exciting stuff, doing the confidence interval itself. This one's rolled into just one part, compute the confidence interval. So if you were going to see a problem like that one, it's good to think in terms of a step-by-step process. And this would be my suggested steps for if you're constructing the confidence interval all as one big part, do this, then that. So step one, probably the best thing you can do is write down the formula. Let's put that down below. The formula for this particular confidence interval goes p hat, add or subtract a critical number, z star, multiply it by the standard error of p hat. SCP hat is just one number together. It's an entire symbol that describes this one number. So once you have the formula down, keep in mind exam 3 will be open notes. So this will be something you might have memorized just by making those notes and writing this down, but it's something that you would double check in an exam setting. Putting it down on paper is worth partial credit already, and it tells you what to do. Going left to right, step 2 should be write down what p hat is. We already got it down on paper, so there it is. But just for the sake of the step-by-step process, let's say it here. Step 2, either compute or write down p hat. Let's say it this way, compute p hat. We actually had to compute it in the last problem because it gave us a sample size and then a number of successes. So we compute it from scratch, but in this problem, they just told us what it was. So let's just copy it down. P hat is 0.2035. Step 3, you could compute z star right here from scratch if you wanted to. But I mentioned there's 3 very common level of confidences, 90%, 95%, and 99%. And there's nothing wrong with 98% or 96%. But since those values are so standard, we seem to like round numbers like those for some reason. In an exam setting and even on a quiz, it's going to be those 3 values. So step 3 is really look up z star. It's a literal table lookup, so that's kind of nice in a way. This doesn't work in chapter 14. In chapter 14, step 3 is going to say compute t star. We have to do it from scratch every single time. But if you can get away with a simple table lookup, that's worth just taking advantage of that. So go to the top of the notes here. Here's where we have to scroll. Not the complete top, but here's what we need. Here's that table. This is something you definitely would want to include in your set of notes for exam 3, or else you'd have to compute it from scratch. It's an inverse norm problem. That's just not worth the distraction. So be ready to go with that table. Z star at 99% confidence, our confidence level, is 2.58. So drop down below. We're just putting in 2.58 for that value. So we've got a critical number Z star. Step 3. It's kind of like step 2. It's another computation. Step 3 is compute standard error, or yeah, thank you, step 4. I forgot how to count for a moment there. Step 4, compute the standard error of p hat. So this is a formula you're going to definitely want to have ready to go. Standard error right here of p hat goes square root p hat, 1 minus p hat, divide by n. There's a lot of computations that happens on these problems. So anything you put on paper, if it's correct on paper, this is a major amount of partial credit. So let's write it down as we're thinking about it. 0.2035, 1 minus 0.2035. The reason I give this so much partial credit was when I first graded these kinds of exams, when I got just the numbers, it felt bad to take off a lot of credit when I had no clue how we got those numbers. So this right here on paper is worth a lot, even if you make a silly mistake in the calculator. Sample size n, let's scroll up, is the 339, so let's drop that in. I think we usually kept that in black, so let's keep that pattern. Now we've got a value. We just throw this all into the calculator. And it really pays to do this as efficiently as possible, so we're not getting bogged down on computations. To me, this is the fastest way to calculate standard error in the calculator. Put in 0.2035 first, and just hit enter. That seems kind of weird, but the reason you want to do that is it's now stored in the calculator. Now call the square root, second, right here where the power 2 button is, then hit up arrow to import that number, parenthesis, up arrow again. Hang on, let's not jump the gun. Go to the parenthesis and go 1 minus, copying that format. 1 minus. Now go up arrow to copy that in. Close the parenthesis, divide by 339, the sample size. And we've got a value out. We're rounding to 3 decimal places, but this is a computation in the very middle. Because it's an intermediate computation, best practice here is to go for 4 decimal places and then round your final answer to the 3 places, just to make sure you're just a little bit more accurate. So to 4 decimal places, this is a 0.2189. 0.2189. So we've got the formula down. It told us what to calculate. Those were the next steps. And essentially the final step is, I guess, depending on how many steps you want to list, the penultimate step is substitute in the information. Let's call it step 5. Oh, hang on. I think I see what you're seeing. I kind of copied that down wrong. There's a 0 first. Let me try again. 0.0219. I'm not too sure what I was writing down there. 0.0219. Let me double check the work there. Does that look better to folks so far? Awesome. Thanks for indicating that one looked kind of weird on paper. So next, on step 5, all we're doing now is, let's say, substitute in the values. So that means we're going to get where this was, it's now equal to, in step 5, 0.2035 for the p hat, add or subtract, z star, that's the 2.58, which then multiplies standard error of p hat down here, 0.0219. And we're just about there. We substitute in the information, and as a step 5, compute the values. But here's where it gets really interesting. These values are estimating one thing in particular. It's estimating p, the unknown parameter, the true proportion of adverse reactions to that vaccine. So when you go to compute the values, there's several ways you can write this in. Let's write it in as inequality form, just as a direct reminder, that's what we're estimating, the parameter P in the middle. So write this in with a negative sign first, 0.2035, go minus 2.58 times the 0.0219. So this is our lower value. This one's rounding to 3 decimal places, so this is a good time to do it. 0.147. So that goes in right here. The standard trick is to up arrow twice to now import the entry that you had in. Hit enter to drop it down and flip to the positive sign in the middle here. Gives you the upper bound, 0.260. Even though we're rounding to 3 decimal places and that's a 0, it's a good idea to put it in just as a reminder. That's the next value you would have gotten with rounding. So there's the full 99% confidence interval. I want to mention that, again, we've said this before, when you put this in MyLab statistics, it's going to give you an interval like this. It looks like this format. You just fill in the lower bound and the upper bound. So you'd put in the 0.147, and then the upper bound, 0.260. So that's what it looks like as a MyLab problem. Let me make sure that actually looks like a 7, though. And you're free to do that as well. That's the actual mathematical interval using interval notation. This is the same information in inequality form. The reason I like to personally emphasize this a little bit more is because it's reminding us what we're estimating in the very first place, the parameter P way up at the top. But we did it, folks. If you break it down into steps, there's quite a lot, 5 steps. But we made this really, really granular. Step 1 was just the formula. Next 3 steps were just each of the parts. Then the substitution and computation. Really, it's not as bad as it seems. And the more you practice this, the more cleaner it becomes as just kind of a routine of doing these. The other nice thing about this is we're going to practice it again with this different kind of confidence interval. It's just a different statistic, different kind of critical number, but same idea, and slightly different standard error. So we practice this kind of stuff quite a lot. Well, any last questions, folks, so far before we go to interpret this one? Okay, so let's give our overall interpretation. It's really right here, but the problem with this as a confidence interval is if you did this study, if this study is really important to you, and it was to the people in 1974, imagine it's something more recent, then you wouldn't want to go on the news and tell people or write a study in, say, some news magazine and tell people, or a blog or anything like that, that with 99% confidence, 0.147 less than P less than 0.260, because then people will think that you've lost your mind. They're not going to believe any of your results. It's just a terrible way to compute or to communicate what we've actually computed. Mathematically, it's correct, but for a practical interpretation, we have to make some big changes. So that's what we'll do very next on part D. You go back to the original part of what you said P was in the very first place, look up the level of confidence once again, and start off by saying this. You can say with 99% confidence, or we can say we have 99% confidence, or we can say that as your last statement, that there's this estimate and we are confident in this by 99%. You just have to make sure you say it at some point because the interval is different at different confidence levels. So let's go on to say, just so I don't forget, I usually start off with this statement. With 99% confidence, after we pull in the confidence level, we now focus on this part right here. Let's just circle this temporarily to emphasize. With 99% confidence, P is in the middle, but we have to directly tell people what that was. The true. And we mentioned before, you can say either proportion or percent. It's completely up to you. I looked at percent again on this problem, so let's go with the proportion version this time. On the next example we do today, we'll turn it into a percent, just to emphasize that's a fair way to do it as well. So the true proportion of adverse reactions to the vaccine for, I'll abbreviate this part and just say for all infants. Again, you don't have to mention every shred of the context. You can leave some of the original problem to carry some of the weight. We know it was all infants relative to wherever that study was located in, turned out to be Great Britain. So true proportion for adverse reactions to the vaccine for all infants, that's P. Then we just say the other part of this inequality or this interval, whichever side you're looking at, we can say is between 0.147 and 0.260. And that's our entire interpretation. If you said percent here, then you would have said 14.7% up to 26.0% would have been the change. So we did it, folks. That's our second run through a confidence interval. This one's fun because it's actual real data. The last time we did it was just a made-up scenario just to focus on the major elements of the formula more than anything. When they did the study, I'm not sure what kind of confidence interval they would have produced, but if they went for 99% confidence, these are the values they would have gotten to 3 decimal places. Well, any last questions at all, folks? Concluding with this one. Yeah. Yes. Oh yeah, versus the quantitative.
But we haven't done that yet, right?
That's right. So for quantitative, that's when the parameter is mu for the population mean. So that's if we're talking about, say, mean height or mean amount of time, a mean amount of distances. And that's going to be our chapter 14 coming up. But that's a great concept to connect with this. Exactly. And it's actually pretty restrictive because this data is categorical, like you're saying, but it has specifically 2 outcomes, success versus failure. But the good news is we can extend this pretty fast. It just goes beyond the sections of our class. If you're taking more statistics, you can have 3 categories: yes, no, maybe. Maybe it's polling data. It's a procedure much like this, but it just gets called a chi-squared procedure instead. So this starts to get more and more involved. You can also take 2 categorical variables simultaneously, and it's just another chi-squared procedure. But this is kind of like the major one that we look at, where it all starts, the first part for categorical data. But other questions about that so far, or otherwise? Okay, thanks for mentioning that. That's a great connection with what we did here. That's also what's really restrictive about the method. Has to specifically be categorical data, like you said, and only 2 outcomes. Well, we finished the method, but there's a lot of concepts when it comes to confidence intervals, like we mentioned last time. So let's look into a couple more concept questions, parts E and part F. These are questions that I wouldn't ask on quizzes or exams. An exam problem is going to be something kind of like this, where I would skip the condition checking. That's a whole different problem in its own right. So this is about what an exam 3 question would look like, or a final exam question would look like in this section. But MyLab goes a little bit further. They're asking you about certain concepts relating to this kind of information. They're important to think about. And so to help out with the homework, that's what the concept questions down below here are all about. So we have a confidence interval. Its width is from 0.147 to 0.260. Half of that width is the margin of error. And we're being asked, if the sample size were to increase, would this interval, the one we got here, or maybe you're looking over here, would it be wider or narrower? Kind of a tough question to explain.
No,
Yeah, I would agree with you, but our gut kind of tells us that larger sample sizes are better, right, in a certain sense, as long as it doesn't violate the 10% condition of section 13.2. Samples can't get too large. That's the confusion there. But aside from the 10% condition, a larger sample is better. And better for confidence interval means narrower. It means your estimate is better. If this was, say, from something like 19% to 20%, the study seems like it was more successful, but the sample size would have had to have been larger. So that's the major concept. For a larger sample size, the interval, let's say in full, just to be specific, the confidence interval becomes narrower. So in our heart of hearts, I think everyone would believe that. That's got to be true. But explaining it is something else. Let's do the explanation just to reason why that really has to be the case. You have to think about what is the confidence interval. It's this formula right here. And to get the number 0.147, 0.260, we were adding and subtracting this quantity, the margin of the error. This controls the width. So we can say here, from the concept we saw before, half the width of the interval p hat plus or minus z star times the standard error of p hat is the one in this color. Actually, let's go for this pops a little bit more, is the margin of error, m. And m is z star times standard error p hat. Or in other words, if you expand this out, m equals z star. Z star doesn't change on the sample size. It changes on the level of confidence. But the standard error of p hat does change. It's defined to be square root p hat 1 minus p hat divided by n. So if this is the formula for half the width of the confidence interval, take the center, add that value, the margin of error m, and you've got this number. So that's why it's half the width. If the sample size gets larger, the width, half width, should get smaller. And we can directly check that in the calculator. Go back up to this line by hitting up arrow. That's when we calculated the standard error right here. Let's hit enter. Now let's imagine we had a gigantic sample size. If they had the funding to do this, they might have taken a sample size of 30,000. We've discussed the population is large. We range from estimates between about 700,000 to about 3.1 million. So 30,000 kids doesn't violate the 10% condition. Bump up that sample size a lot, and here's your new margin of error. Well, a part of it. This is before multiplying by z star. It's now 0.00232. This was 0.0219. So it's quite a bit smaller. Maybe not as small as you might have expected. The square root is part of a problem here. When you put in the sample here and you square root that sample size, the reduction doesn't happen as fast as we would like it to. The square root is kind of punishing in a way. Sample size has to increase a gigantic amount to make this quite a bit smaller. But it did get smaller, about 1/10 of its size, when we went to a sample size of 30,000. So that's their logic on this one. Larger N makes M smaller. And so the interval narrower. And that's great. We want the narrower confidence interval. We pay for it though. You have to now select a larger sample, and these are very, very costly to do. 30,000 would have taken a gigantic force of people to do. It might not have been completed in 1974. If your study goes for too long, the relevance starts to get lost. So the next concept question is about the level of confidence. We did a 99% confidence interval, and it went from 0.147 to a 0.260. And this is a good one to think about and pause for a moment. If we decided to be less confident, 95% confident, that's a bad thing, right? Higher confidence is better. Confidence means that this is the success rate of the whole procedure in capturing the unknown parameter P within our interval. We want that procedure to be highly successful. So if we say we're dropping our procedure success rate from 99% down to 95%, what would you all think would happen? Would the interval become wider or narrower? That's right, it becomes narrower in that case. Being less confident means there's less of a chance you captured P, and that happens when it gets narrower. And that's a humongous conflict because we want narrow confidence intervals. That's a reason you want to increase the sample size to make the interval narrower. But you can make your interval narrower in a second way, lowering your confidence level. So if we made this study with 339 children, but we decide to do a 10% confidence interval, the math would support you. You could calculate that. You'd get a very narrow interval, and it looks like your results are amazing, that your statistics were so precise because your interval is extremely narrow. Means you have a small margin of error. But if you never mentioned we're only 10% confident, we're being extremely dishonest and unethical with statistics. And this is the major reason we have to say what our confidence is to nail it down so people are aware we didn't do something funny and make a 2% confidence interval just so that our estimate interval itself is so narrow to make it seem like we did a precise computation. So this is absolutely correct. Lower confidence means a narrower interval. And this is in part the justification of why we always state the level of confidence. So if we have a narrow interval, but at 99% confidence, now we start to trust the results, trust the data, that nothing is being kind of put over our heads. No one's essentially lying in a strange, sophisticated way. And here's the justification. It's all about the margin of error, M once again. M equals Z star times standard error P hat. So this controls half the width at 99% confidence. M is equal to, let's take a look. I forget what the Z star was. It was 2.58. So N becomes 2.58 times the same exact standard error. The standard error doesn't change this time if all you're changing is the confidence level. And now at 95% confidence, so we decreased it down to 95%. M, take a look at that table again. Z star is a 1.96. So it'd be 1.96 standard error P hat. This controls half the width, so this gives a narrower interval, which deserves an exclamation because, again, that's a sort of a concern because it's a conflict of what we want. We actually want higher confidence and a narrower interval at the same time. So decreasing the confidence to get to the narrower interval is not the way to go. To make the interval narrow, really there's only one thing we can do. We have to bump the sample size. We have to pay for the study, and sometimes we have to pay a lot of money for that narrower confidence interval. But those were the two additional concept questions to tack onto the problem, just like on the first example, or example 2 that we did on these notes. For the next example we're going to take a look at, it's just going to be run through the start to the conclusion. This is the end of those strange concept questions. Any questions at all about them so far?
The first 2 questions too,
Sorry, say again?
on the homework.
Oh yeah, these come up in my lab. Yeah.
Right out the gate.
Gotcha. So yeah, like Bryce is saying, watch out for these kinds of concept questions in the homework. I think they're tricky if they're kind of right out of the blue. You could come back here for some guidance on how to get through them. Okay, let's try out our next problem then, the last one for these notes. After this, we'll be turning it over to the quantitative data sets. So this is a brand new problem. And it seems silly at first, but it's a very serious context. So this is something in 2003, so it's starting to get kind of old. It's still decades old data, but more recent. We're told the technology underlying hip replacements has changed as these operations have become more popular. In the year of 2008, there was 250,000 hip replacements. And this is a pretty traumatic event, so you want to get it done right. So next part of this medical study tells us in 2003, highly durable ceramic hips were marketed. So you now have something indestructible as your new hip bone. That sounds great. You never want to have a total hip replacement and have the thing break on you. That would be like your last chance at life at that point. That'd be the worst thing ever. So we have extremely durable ceramic hips, but here's the trade-off. After they released these in 2003, it says, unfortunately, for too many patients, the increased durability has been counterbalanced by increased incidence of squeaking. And it seems silly at first, but you have to imagine this is something that's attached to you for the rest of your life. If that squeaking is just the right amount that it drives you insane, you might have not wanted the ceramic hip in the very first place. This could be grandma literally losing her mind. We don't know what's going on with this, but this was serious enough for a study to investigate it. So we're back to 2008 when there's 250,000 hip replacement surgeries done, probably a good amount of them, the highly durable ceramic hips. In an issue in the New York Times, they reported that in one study of 143 individuals receiving the ceramic hips, between the years 2003 when they started to 2005, these are the new ones, the first generation ones, the ones that are probably not as refined yet. 10 of those people, now 143 individuals, had hips that began to squeak. And they're squeaking forever by the sound of this. So every time you bend over, every time you say, try to grab the ball for the dog, it's going to make a sound. So this is the full context. Lots going on in this one. It's a new set of context. But right here, when it says 143 individuals, they at least told us exactly sample size N is the 143. These are the individuals with the ceramic hips. Let me fix my penmanship here. This is categorical data, and to really see it, you have to say, what is a success? Any volunteers for saying the success in this problem? Exactly. A success is the outcome, I'll say it the way you said it, is the outcome of squeaky hips. Again, you have to really treat this data seriously. The first time I read this, I thought it was silly, kind of funny, but the more you think about this, If it were me, I'd probably start losing my mind by about year 2 of hearing that same sound over and over again. So this is what the study is all about. Categorical data. Once you know what the success is, it's not a bad idea to say it again. This is kind of a hint, right? You know what the sample size is, but a smaller amount of that sample has a particular condition. That's the giveaway. You're looking into the successes. So we can also say 10 successes in this sample. Let's highlight that just to connect that thought. From here, we can start out the problem. We want the unknown parameter P. We need to mention 2 things. In any order, you can mention the population first, you can mention the successes first. It's really up to you, but they have to be in there some way, somehow. And we mentioned before, when you say proportion, that's a synonymous word to percent. So if you decide to call this P equals the population percentage, that would be completely fine as well. We did population proportion on the other problems. So to just show a different way to do it, let's go for percentage on this one. So the population percentage of, let's say what the successes are, squeaky hips. Among all, once we start to say all, that's kind of a giveaway. We're talking about the population. And what would you all say the population should be in this case? Exactly.
Did you just say hip replacements, or would you wanna see like for all people that? You wanna say anything like that?
I would probably want to be more specific on this one. In an exam setting, if you said among all with a hip replacement, I would probably give that full credit. But if you're thinking, it's not just about a hip replacement, right? It's certain ones, the ceramic hip replacements, I would consider that to be the best answer. So let's say it that way. Among all patients, forgot how to spell patience out of nowhere. Must be getting late. Let's say for, sorry, say again.
It does say the 143 received ceramic hips.
Yeah, that's kind of a giveaway. That should be in the population because if everyone had ceramic hips in the sample came from the population, they all have the ceramic hips as well. So we'll say among all people with a ceramic hip. And here's where I mentioned a lot of times with parameters and populations, you can be hyper specific. It's hard to know where to draw the line. But when it comes to medical technology, it's a moving target that changes every single year. They launched the ceramic hips in 2003. I bet you in 2004, 2005, they started to change just a little bit. And I bet you the hips in 2008, even if they were still ceramic, it wasn't the version 1 ceramic hips. I bet you they were a lot different in 2008 when they started installing these new batches. Medical technology is constantly refined and changed as it goes, much like cell phone technology, just for an example. And so if you want to be really specific on this parameter, you would say for all people with a ceramic hip, how should we say this? With the procedure done between 2003 and 2005. That might be really, really important because the ones in 2008, probably they might squeak, but I bet you at a very, very reduced rate. Maybe they don't squeak at all. They kind of hammered out that issue. But if this was an exam question and we want to mention the context, you have to say something about the successes. So we've got that in. You have to say something about the fact that we have a hip replacement. Well, we kind of said it in a separate way when we said people with a ceramic hip, implying that that was their hip replacement. So if you just said people with a hip replacement, I would have said that's okay in a, say, exam 3 setting, final exam setting. But this would have been the better answer. And if you didn't put this part in at all, well, it's actually in the overall context, so that would have been okay. We're just being more specific on this particular problem. Well, any questions at all, folks? Nailing down this one, this parameter? Okay, they're tricky things, but we'll practice this some more when we're in chapter 14. We'll practice it all over again when we're in chapter 15. We'll look into both the quantitative data and categorical data like this under a new procedure, hypothesis testing. So this is not the last time we'll see a parameter like P. We'll look into it again in chapter 15. But now we're breaking down the confidence interval procedure into just parts. These questions can be asked in different kinds of ways. In the last example, I just said, construct the interval. So we did all the parts right here. In this problem, they can be written in different ways. It's giving us all the components. We'll do the sample proportion, the standard error. Then down here, we'll look up Z star and just put it all together. So this one is just a little bit more broken down. When it says sample proportion of successes, exactly, this is our p-hat part. We take the number of successes in the sample, 10 of them, divide by the sample size, 143. So that's our formula. Let's throw this into the calculator to get a value out. 10 divided by 143. It's a small proportion and a small percentage of the sample. I mean, that's a good thing. This is something going wrong with medical technology. But if we're rounding this to 4 decimal places, it's a 0.0699. Next, let's look into the standard error. Standard error of p-hat. This is a good one to just write in the formula in for extra practice. P-hat, 1 minus p-hat, divide by sample size n. What we'll compute is this, 0.0699, 1 minus that same value, divide by sample size n, which is 143. So now it just gets thrown into the calculator. But it's already in the calculator. It's right exactly here. So let's use that idea of there's fast ways to compute this. Hit second x squared button for the 0.0699. Let's drop in this whole thing, unrounded, slightly more accuracy. Hit up arrow and enter to copy it in. Open a parenthesis and go 1 minus. So that's this 1 minus part. Copy in the same number as before. So up arrow, enter it down to drop in that number. Then divide, double check when you're dividing that you're inside the square root, that this bar keeps on extending for you. Divide by 143. And that's our standard error. Also to 4 decimal places, it's 0.0213. So we're getting through it. Any questions at all, folks, with these 2 computational parts? Okay, now we're going to check the conditions briefly. It's not mentioning the conditions of the central limit theorem, of which we checked 3 of them specifically. It's just wondering, was the sample random? And do we have enough successes? We need 10 successes, 10 failures. First, let's look into randomization. Reported that in one study, 143 individuals received a ceramic hip. Once again, another study with no reference whatsoever to randomization. So we just mentioned that down here. And this part right here will say there is no information given on randomization. That's unfortunate. I believe some of the problems in the sample exam that we're going to look into And even on the quiz problem, it might give us information on randomization. I'm noticing this is a pattern in the notes. All three problems that we did had no information given. So what it would look like if information was given, let's see what quiz 9 looks like. I feel like we need to have a win here somewhere. So it says here, assume that 220 people in the film crew can safely be considered to be a random sample. Well, that's a roundabout way to say it. It looks like it wasn't a random sample, but maybe they looked into the demographics and it's representative enough so it can be safely considered to be a random sample of all people exposed to the same level of radiation. So this is about John Wayne and his film crew that shot the Conqueror at the same time nuclear testing was being done in Nevada. That was a very sketchy thing that we would never do in this day and time. But that's what information would look like if they're trying to tell you something about randomization. For some reason, I didn't think about this until we launched the problems. Just didn't seem to be mentioned in our three examples. But the thing that we can check is successes versus failures. We already know we have enough successes. There are 10 successes as required. What I mean by that is, if we look back to the confidence interval procedure itself, sorry for the random scrolling, the benchmark was right at exactly 10 successes. Our sample size is actually pretty small at 143 people with ceramic hips because we barely passed this. We are right on the boundary, but at least includes equality. So we have a pass here, just barely. This is the reason it's called a large sample confidence interval. If you're studying something that's kind of rare, like medical technology randomly being on the fritz, these are rare occurrences, and sometimes your samples could have been in, say, several hundreds to have done the study if it was something even more rare. We barely made it in our study with 143 observations in the sample. So we have 10 successes, and that means we have more than 10 failures. My penmanship is kind of disintegrating. Let me try again. There are, take the sample size n minus the number of successes, 10, 143 minus 10, 133, which is definitely greater than or equal to 10 failures. So our sample size is barely large enough, but it qualifies. This is a pass. The sample size is large enough. So the additional comments that we've often made is the conditions are met only if the sample is random. It can't just be any 143 people who had the ceramic hip replacement. It's kind of interesting how they might have gotten these individuals. But if they can justify that this is or at least representative of the entire population of people with the ceramic hips in these 2 years, then this condition would have been met. Now we're going to put it all together and compute the entire confidence interval itself. But any questions at the moment? Okay. Well, first thing we'll do is we're going to need these two values and a third value. When it mentions 95% confidence, you might have already memorized the number. The number we need is Z star equals 1.9600. But just to emphasize where we got it, we went to the near top of the notes. Sorry for the random scrolling once again. Match up the confidence level with the critical number Z star. You don't have to compute it from scratch, but if you did, you would come out with the same number, rounded to this value, to 4 decimal places. So go to that table once again. It's something you'll definitely want to have on your notes when you do the exam 3. And now we have all three parts that we would require. We have p hat, standard error, and z star. Next thing to do is just write down the formula. It's p hat, add or subtract z star multiplied by the standard error of p hat. So this turns into, first drop in p hat, 0.0699. Add or subtract this number, 1.96. And then finally multiply it by standard error, this last substitution, 0.0213. When we get the interval, we're placing p in the middle. At first, it's going to be a proportion, but we'll convert it into a percent as an additional step because we're going to write out a conclusion mentioning the percent. So back to the calculator, we're nearly through this one. It goes 0.0699. Do minus first to get the lower bound. 1.96. 0.0213. So here's the lower bound, and the lower level is, we're rounding to 3 decimal places, 0.028. So the true percentage of squeaking hips is at the low end, about 3%. If our procedure was successful, and it succeeds 95% of the time. Now, up arrow, so you don't feel like you're doing this twice. Scroll over to here, flip to positive, and now you're just doing this upper bound right here. On the upper end, it's not as pretty as a picture. It's as low as around 3%, but it's as high as a little over 11%. This is 1.112. Then multiply all three sides of this inequality by 100%. It moves the decimal places 2 spots to the right. And we get a confidence interval that goes from 2.8% less than p as a percentage, percent sign just to emphasize, we're giving the percent value, less than 11.2%. So that's our confidence interval. We didn't quite make it. I don't think we want to rush through part F. So we'll kind of refresh this when we come back on Thursday's class. Look at how we did this interval, give the complete conclusion. Then we'll jump into chapter 14 and turn it all around to quantitative data. But that just means we're doing the same kind of thing, slightly different formula, but same exact parallel kind of format. So we didn't quite make it to the end of this one. We'll come back to it first thing on Thursday's class. But any last questions or comments, folks, getting through this so far? Okay, well, our upcoming exam 3 is Monday, November 17th. The information's posted early. Best way to get practice on this is give quiz 9 a try, do the MyLab statistics homework problems. You'll get a really good idea of what's going to be on that third exam. But have a great night, folks. We'll be back to this on Thursday's class.
Quiz 8 will be on exam 3, right?
Yeah, this one is going to be the chapters 10 stuff. And similarly with quiz 7 on the chapter 7 stuff. The only thing that didn't come in as a quiz is the 13.2 problem, where we're doing this kind of condition checking really carefully.
Oh,
So that's the only one out. So we'll probably make sure we do something like this when we do our review next week.
that will be on the exam.
Yeah, 13.2 will be one problem that is on exam, but it didn't have a quiz to go with it. Oh, awesome, thanks. Yeah, as far as the exam goes, it's going to be 3 chapters, but 4 questions, just like the other exam. And chapter 13 is the one that's going to have 2, the condition checking, and then the problem like we just did.
Oh, it's good.
Exactly, yeah. I think the other ones were 4. I'm honestly starting to forget.
30, but
Not quite. I think for our final exam, It's 2 hours, but I usually get it down to about 12 questions. So it can't be everything we did in the class. It's gonna be like selecting just the major ideas, the main things that we did.
Okay.
And I was mentioning to Christian earlier as well, a good hint on what's really gonna be on the final exam is we'll have about 13 to 14 quizzes by the time we're way down here. Put all of your quizzes together, and that's basically a sample final exam. Those are meant to be kind of the main summary ideas. But we'll also look into other stuff. I'll be posting several things down here for additional practice. Yeah, that's right. As Coral was asking, the final exam is Monday of the final exam week, and that means our course ends pretty much on that time. So I won't have any classes for us on Wednesday or Thursday, our finals week. But if you did have questions by email, anything like that, I'm still available on Wednesday, Thursday. I wouldn't have office hours, but I'm not going to ghost you just because we got through finals. So you can still reach out, ask questions. Reason that might be relevant is I finalize my grading on Friday of finals week. So if there's any last things that you want to get in, maybe a last quiz that you might have missed and you're turning in very late, best time to do the quizzes before finals for practice. But anything that was left hanging on my lab statistics or final quiz, the final deadline is going to be our last, if we did have a class meeting, Thursday of finals week. So there won't be any meetings, but you might still be doing stuff potentially.
Just so that we like reschedule the final earlier.
Yeah, I think we did mention that on the first day. Thanks for the reminder. This is like the most brutal time ever. Someone in Pocatello, the registrar's office, scheduled this for everyone in Idaho Falls. So if this doesn't work for you, I am giving other final exams and we can work something out.
4 AM.
4 a.m., that would be a rough one too. Yeah. You know, I wonder, some people might do better at 4 a.m. versus 8 p.m. when it comes to that kind of stuff. Some people just wake up, drink a couple pots of coffee, and they're ready to go. But then they're crashing around this time. Well, any last questions at all, folks, before we call it a night?
Is it 8 PM?
In this room, yeah. Wild time, isn't it?
They've almost wiped it. Are you gonna be here for it?
I am, yeah.
Why wouldn't they just let us keep our regular class time?
The idea is the registrar tries to do a final exam schedule that has the minimum amount of conflicts possible. And because the exam time is 2 hours, way beyond the ordinary class time, there's a group of people, a cadre of people in Pocatello, the registrar, highly paid administrators, that devised a scheme to ensure that there's never going to be a conflict between one class and another. And they spread out exam times really far for that reason. If you're a night class that does Monday, Wednesday, Thursday, or Monday, Wednesday, Friday, like in Pocatello, this is the time slot they throw us in. And even though they work really hard on that, people still have conflicts. So you might want to check your final exams if you're taking multiple classes. You might actually have a legitimate conflict on your final exam time. But every professor just works out some kind of different time, kind of different deal. This stuff happens. But I agree with you. That is like the worst time ever.
I'll be here at 12.
I will be here too. Yeah, that'll be my job.
Do it.
But if anything happens, if some people can't make that time, I'm giving other earlier times as well.